Working now. Yeah, so I'm presenting from Jupiter Intelligence. I'll talk a little bit about our company in a minute. Because we're talking in the Views from Domain Size session, I want to give a perspective from a private sector company that's involved in climate analytics. Because we're interacting with a wide variety of customers and end users with global interests, this can impose some unique restrictions and concerns about how we develop our methods, particularly where machine learning and AI are concerned. So I want to touch on those concerns a bit in this talk, but also give you a flavor of the kinds of machine learning AI projects we've been working on. So what is Jupiter? We're about a 4-year-old company based in the United States, and we're growing quite rapidly. We've got a science-forward approach to what we do, which is mainly to survey the climate community for the latest and greatest methods for understanding the current climate, know what we can and cannot say about how the climate is expected to change based on the latest science, and then find the most promising methods for answering climate-related questions that our users are asking. We then use those methods to try to present a clear and open view of how climate change might affect these end users. I say open to really highlight that we view communication about uncertainty as essential to building and delivering our products and analyses. So all of the models we use have to provide a clear view of uncertainties around climate change and propagate it to the best of their ability. The kinds of projections we do have an operational capability, so we can provide forecasts on the hourly to daily time frame. But the majority of the analyses we produce are on the multi-annual to decadal scale, looking at how climate change will occur over the next tens of years out to 2100. We model a number of perils. I have listed several on the right, though that list continues to grow as additional customers and users ask us new questions about new things that are relevant to them. Our users come from a wide number of sectors. We list several of them here at the bottom of this slide: energy, engineering, reinsurance, local governments. So we get a diverse set of requests from a large number of people about what we can tell them about how climate change is going to affect them. So how do we do our analyses? This schematic at a high level highlights this process, going from inputs at the bottom to outputs at the top. It starts at the core with climate data. We've curated a collection of what we feel is the latest and greatest of the climate data that the academic and government laboratory communities have produced, and supplemented with some of our own simulations and data that we produce in-house. This data includes some of the classics, CMIP 5, CMIP 6, global climate model projections. We've also worked with academic groups that have run various large ensemble projects, dynamically downscaled data sets, and other associated projects related to the global climate modeling effort, like the Cordex project. We bring in a number of observations for both validation and bias correction of our model outputs and future projections. As I mentioned, we also can produce our own downscaled data sets. And then we also include a number of predictors or other variables that are relevant to understanding climate at a local scale, such as elevation models, land surface characteristics. We're a cloud-native company, so all of this we have stored in that cloud-optimized formats on a cloud storage bucket. With this data, the methods we use to produce our analyses range from primarily traditional statistical and dynamical downscaling techniques to talk about climate change on a local scale. On the statistical side, we use methods such as extreme value analysis, non-stationary distribution fitting, analog finding or analog mapping, to produce some fairly traditional statistical downscaling products as a part of our output. On the other side of the spectrum, we also have the capability to do dynamical downscaling. We have a number of geophysical models that we have containerized and placed on in a cloud-optimized format. These include meteorological models, hydrologic models, hydraulic models, coastal ocean models. We do a lot of flood modeling, so that whole class of models is captured there. And then these two methods of producing downscaled climate projections kind of map onto the two main categories of products you produce, which is this outer band here in this image. On the left, you see with the little globe icon, portfolio level aggregation. These kinds of products are primarily statistically downscaled products, and they span the entire globe. These are mainly for our users and customers who have global spanning portfolios, and they're interested in looking at, say, for my list of 1,000 hotels across the world, which ones are going to be more susceptible to flooding, or which ones more susceptible to extreme heat. On the other side, we can also do these, and here it's called asset level drill downs. We call it a localized planning sort of product. These are for customers or users who have either assets clustered in a particular location, say a particular city, or local governments that are interested in how climate change will affect their particular localized area. For those kinds of analyses, we primarily use dynamical downscaling. So we'll use, say, the weather research and forecasting model to downscale meteorology, and those various flood models I mentioned to look at, say, flood risk. Machine learning is not the core of our methods. We use it, it is still definitely a part of our toolkit, but we've deliberately chosen not to make it the center part of our methods and instead are relying on these more traditional methods. We do use machine learning, however, to try to push these analyses to the next level, to answer specific questions that these other analysis methods just can't seem to really tackle, or where we think there's a unique advantage that machine learning and AI techniques can provide. So when do we decide to use these kinds of techniques? One of the nice things about Jupyter, we've got a great team of scientists, and they span multiple disciplines. So we've got people who are traditional data scientists, we've got a number of climate scientists, and we also have scientific software developers who are familiar with a lot of the ever-changing and emerging toolkits that are out there to do machine learning and AI. And together we've come up with a list of a number of tenets that we consider when we're trying to decide if a machine learning or AI approach or solution is the best way to handle a particular problem. I want to highlight a few of these here, and particularly the three that I've bolded in this slide. I'm going to come back to at the end because there's some unique caveats being a private sector company working with customers that cause us to really think seriously about those three. Just to run through these quickly. First, though, we want to balance established and cutting-edge techniques. Like I said, we're primarily using well-vetted, peer-reviewed models from a statistical and dynamical downscaling perspective, and that lends a lot of credibility to that analysis. We still want to push the edge with some of these unique, more modern methods, but there has to be a compelling reason for us to do so. There need to be clear expectations of the potential for success, and this is where domain expertise becomes very important. As a climate scientist, I often will have a mental map in my mind of this set of predictors should map onto the kind of analysis result I'm expecting, and I have a mental image of how that mapping should work. If I'm going to go and use a machine learning or AI technique to try to model that mapping, I have to choose a method that I think is going to most closely emulate that to guarantee success. We're not just going to throw all the tools in the toolbox at this problem, loop through everything in some library of machine learning models and see what happens. We have to really carefully think through and think what method is going to give us the best chance of success. We want to maintain quality. It seems like a pretty easy one, but we're not just going to do machine learning for the sake of doing machine learning. We've got to be able to show that these kinds of models can produce consistently better or at least equal quality results to these more established techniques for us to use them. The models need to be efficient and deployable at scale. Not only from the technical perspective of being able to churn through the large amounts of training data and produce a lot of output, but also we've got a global reach. We have customers who are interested in various climate analyses globally. So these models have to be able to be generalizable enough that we can deploy them to do analyses at various locations globally with similar expectations of their quality. And then explainability and transparency. This is becoming more and more important as more and more people are looking into climate analytics to answer problems, particularly regulatory concerns. We need to be able to explain why the model is doing what it's doing and how it's, at a high level at least, functions for people to be able to trust those models and the data they produce. So if we can meet those criteria and understand that machine learning is a viable alternative for us, I want to show just a few examples of the kinds of projects we've been doing at Jupyter that use machine learning and AI techniques. One example here is urban scale downscaling. So this is for one of those asset level or city level projections that we do for extreme heat. And we're looking at maps here of just relative differences in warm versus cool areas. When we do this analysis, in this case for New York City, we start actually with a traditional dynamical downscaling approach. Using reanalysis data sets or global climate models that we've bias corrected as boundary conditions, we feed them into a meteorological dynamical model, a bunch of compiled Fortran code that we run at scale on the cloud, and do dynamical downscaling to kilometer scale resolution, which kind of produces the second plot that you see there. Now, as someone with a meteorological background, I love kilometer scale resolution. I wish all of our forecasts were at kilometer scale resolution. But when we go and talk to our customers who are querying dozens of points within the city of New York or the island of Manhattan in the middle, if you zoom in to this next panel on the right, at 1 kilometer resolution even, Manhattan Island is not well resolved. You get a general idea of the pattern of what heat looks like there. But we know more from in-situ observations, from satellite-based heat maps, that there's a lot more variability in heat that we can actually estimate. So we built a random forest-based machine learning model to use predictors like land use characteristics, elevation, distance from the coastline, to estimate these relative differences in heat throughout the cityscape and then are able to feed in our 1 kilometer downscaled results to produce more refined maps of how heat varies across the urban landscape. So you see in this final map on the right, we resolve Manhattan Island much better. You can see areas like Central Park in the middle of New York City is highlighted as cooler. There's more vegetation there. It's not all paved over urban impervious surfaces. In fact, most of these blue areas are areas where there's more vegetation. You also see cooling around the coasts along the rivers themselves, which is what we expected. So that was a really nice application of a particular machine learning model. A different topic, precipitation downscaling. This is actually a project that an intern with us worked in over the summer. So we have a summer internship program where we bring in graduate students who work with us for about 3-month periods over the summer. This is Brian Gronke in 2019, who took some existing ideas in literature for thinking about downscaling as a super resolution problem. I saw on the agenda we have a couple more talks that are coming up that are also considering super resolution type methods for this. So I'm really excited to see that this idea has been explored in many different groups. And his basic idea was taking 1 degree scale climate or reanalysis precipitation fields, which are fairly smooth and don't really capture localized extreme precipitations, and building this super resolution convolutional neural network to provide realistic maps of how precipitation might look at a higher spatial resolution that were consistent with these coarser resolution products. This was a generative model, so given the same input coarse resolution product, we could generate multiple realizations of what the finer scale precipitation patterns might look like. Again, this helps us really flesh out that uncertainty we're trying to communicate about extreme precipitation. Now, when this work was published, I have the DOI listed there of the work that he published. Last example I want to show, kind of on the same theme of precipitation. This is another way we're extending more traditional analysis techniques, and this is for generating precipitation fields for synthetic or stochastic tropical cyclones. For simulating tropical cyclone-related hazards at Jupiter, we use a stochastic tropical cyclone model, which is essentially a model that produces a track for a lot of possible tropical cyclones that could occur but may not have been observed. So they give you the locations of the storm, its intensity along the way, but that's most of what they give you, just some general characteristics of the storm. If we want to associate that with a precipitation hazard, we have to consider that precipitation in hurricanes has some complex structure. It's got ring-like features around the eye, often banded precipitation. And so the challenge was, how can we build a precipitation field that looks realistic but uses these synthetic tracks? So this was a collaboration project with Will Kleiber at the University of Colorado Department of Applied Mathematics. He worked with us over 1 summer on this project. We like to have these kinds of academic collaborations with people to help flesh out ideas and develop them. And he incorporated a number of actually machine learning techniques along kind of a chain of different processes, including some principal component analysis, random forests. There's an autoregressive part to this model to build this generative model to produce precipitation fields that look physically realistic and statistically at least match what we expect for tropical cyclone precipitation. So that's just 3 examples of the kinds of things we do. There's a lot of other applications we've used machine learning techniques for, including bias correction, stochastic weather generation, so time series generation, but just kind of the flavor of the ways you decide to use it. This is my last slide. I wanted to revisit 3 of those tenets and elucidate why we really need to be concerned about these as we push forward with these machine learning techniques, particularly coming from a private sector perspective. The first is that reception to these machine learning and AI techniques can vary. Some of our users are really excited when we say, hey, we built this machine learning model that can more accurately predict such a thing. But we have a number of other users who've told us that it's too much of a black box to them, and that particularly if they've got a regulator who's asking them to disclose climate-related risks, if they can't clearly explain why our model does what it does, they cannot use the output from this model. And now, as a private sector company, if your customer is telling us, I can't use your data if you use a machine learning technique, that causes us to really think carefully about what we need to do to either explain that model to be able to convince them it's good to use, or if we're even going to bother with that development. Other users have said they've been burned before with the overpromise of machine learning AI techniques, something that maybe is the fault of a lot of people in Silicon Valley for hyping up that machine learning and AI is going to save the world. And then 3 years later, you're left with basically the same quality of data we had to start with. So there is a lot of skepticism out there. And we as a climate community, if we want to use these tools, we have to be prepared to address that skepticism. This kind of leads to the next point. There's already a wealth of established statistical and dynamical methods available. So why should we commit to machine learning or AI solutions? And that's something I'm going to be looking for in the talks in this workshop, is, why did you choose machine learning and AI for this particular problem? Why do you feel this is going to do better than using existing techniques? It could be cost savings, it could be just the way it processes data, but having that explanation or that motivation is really important for us. And finally, the transferability of the models. Again, our customers are global. They're interested in climate change all over the place. So it's great to see proof of concept models that, predict stream flow for one watershed in central England because that was what you had the training data for and could work on. But we've got customers who are then asking about, what's my flooding looking like in Singapore or Lagos or Buenos Aires? And if we can't take that model and either quickly retrain it or transfer that data to another location, these models have limited applicability to us. So we want to build these generalizable models that can be applied everywhere. So that's it. I think that was my last slide. Thanks for your attention. And if there's any time left after my brief delay in starting, I can take a question or two.